In this video, I'm going to talk about my new method for automatically generating complex shapes using graph grammars. This is a follow-up to my earlier video. My earlier video gives more of a broad overview of the method. You might want to check out that one first. In this video, we're going to dig into the first part of the algorithm and get into more of the details. I'll start at the beginning, explain our goals, explain the idea of gluing graphs together, the graph boundary, and how to organize the possible graphs into a graph hierarchy. We're going to get into a lot more of the details that I skimmed over in my first video. Our goal is to take an input shape and generate a new shape that's similar to it. Imagine we pick some point in the space. We'll call this point P. We draw a small circle around P. The circle has radius r. This circle defines a small region around the point. We said that one shape is similar to another if each neighborhood in one shape matches a neighborhood in the other shape. This is called R-similarity. In my method, I make the radius as small as possible so that every neighborhood will only contain one vertex, one edge, or one face. Two shapes are locally similar if all these small neighborhoods match. When I say that two neighborhoods match, what I mean by this is that one neighborhood is just like translated copy of the other one. I only consider translations in my method. Other authors consider translations and rotations, and it would be interesting to consider rotations in my method. Let's start by defining a few terms. A graph is a set of vertices and edges. If we have a graph and we know the angle of each edge, then this is called an angle graph. If we know the positions of the vertices, then this is a graph drawing. Most of the time, we'll be talking about angle graphs. Each edge in our graph will have a label, and the labels will have angles attached to them. So these are angle graphs. At the very end, we'll think about how to position the vertices. Eventually, we'll turn all the angle graphs into graph drawings, but that's only going to happen at the very end. Most of the time, we'll be discussing angle graphs. For each angle graph, there are many ways to turn it into a graph drawing. When we think about angle graphs, we only care about the angles. We ignore distances. This is similar in some ways to topology. In topology, we care about how surfaces are connected together. We ignore distances and angles. We allow objects to bend and stretch. Bending and stretching does not change the topology. Now we're doing something similar here for angle graphs. With angle graphs, we care about angles, but we ignore distances. So the graph can stretch, but it cannot bend. We use angle graphs as the input to our algorithm. The input is a polygonal shape, and we don't really care about the edge length. So this is a polygonal shape made up of faces, vertices, and edges. We can give the faces different colors. This is very useful for controlling the results. In this example, the inside and the outside of the shape have different colors. So we're treating the inside and the outside of the shape differently. The shapes we generate respect this. But if we have the same color on the inside and the outside, then there's no clear interior and exterior. These colors are very important. Small changes to the colors can totally change the results. Generally, if you use the same colors, this allows for more freedom and more varied shapes can be produced. If you use different colors, this will limit and restrict the shapes you can make. Next, we label each edge. Each edge has a face on its left and a face on its right. We assign a label to each edge based on the color of the left face and the right face and the angle of the edge. Two edges have the same label if they're locally similar. Every edge can be cut in half. It can be cut into two half edges, pointing in opposite directions. We label these half edges A and A bar. The full edge is labeled A tilde. If a half edge is pointed downward, its label has a bar over it. Half edges pointed up do not. So if the angle is between negative 180 degrees and 0 degrees, it has a bar. If the angle is between 0 degrees and plus 180 degrees, it doesn't have a bar. You may have heard of half edges before if you've studied computational geometry. I draw my half edges a little differently from other people, but this is really the same idea. Eventually, we're going to turn our angle graphs into graph drawings, but we need to make sure the angles are consistent. Otherwise, it will be impossible to draw the angle graph without the edges intersecting. Every time we create a closed loop, it must turn 360 degrees. If it turns more than 360 degrees, this graph cannot be drawn without the edges intersecting. The rate at which the tangent angle changes at a point on the curve is called the curvature. The total curvature of any closed loop must be plus or minus 360 degrees. Let's simplify things for a minute. Imagine the tangent angles as being positions on a wheel. Suppose the wheel started at 0 degrees and ended up at 5 degrees. How far did the wheel turn? It could have turned 5 degrees, or 365 degrees, or 725 degrees, or negative 355 degrees. Now, we can determine how far the wheel turned if we keep track of how many times the wheel crosses a particular angle. If it crosses the angle counterclockwise, we call this a positive turn. If it crosses clockwise, we call this a negative turn. We have a similar situation with the angle graphs. We want to compute the total curvature, the total amount that the tangent angle changes along the path. Now, we know the tangent angle of every half edge. It's part of the label assigned to the half edge. But this is not enough information. We also need to keep track of how many times the tangent angle crosses a particular angle. We will use the angle 180 degrees. The tangent angles go from negative 180 degrees to plus 180 degrees. Negative 180 degrees and plus 180 degrees are really the same angle. So we just need to keep track of how many times the tangent angle crosses this threshold at 180 degrees. And then we'll know how much the path is turned. If the tangent angle goes from positive to negative, I call this a positive turn. It looks like a hump. I will use the wedge symbol for positive turns. Tangent angle is decreasing until it reaches negative 180 degrees, at which point it wraps to plus 180 degrees. I call this a negative turn. It looks like a dip. I use the V symbol for negative turns. Positive and negative turns are opposite. They cancel each other out. If a negative turn follows a positive turn, it means we've turned past 180 degrees and then we turn back. The turns can repeat. I will often describe repeated turns by using exponents. Now we have everything we need to figure out how to glue these angle graphs together. I keep track of this information in what I call the graph boundary string. To find the graph boundary string, we trace a path that goes counterclockwise around the graph. We then write down every half edge and every positive and negative turn we find along the path. So the boundary string for this graph is y, wedge, b bar, a bar. The boundary is a circular loop. It doesn't matter where you start, all starting points are the same. So if you circularly shift the boundary string, it still represents the same boundary. So these strings are equivalent. The boundary always loops around the graph once counterclockwise. So if we count the number of positive and negative turns, there's always one more positive turn than negative turns. The boundary path is oriented so that the path always has the graph on its left side. This means that if we go around the outside of the graph, we turn once counterclockwise. But if we have an interior loop, we turn once clockwise. When I use an uppercase letter, this represents a string of characters. When I use a lowercase letter, this represents just a single half edge. Imagine we have two graph boundaries, A and B, and we want to combine them. We could combine them by splicing the boundaries together like so. When we splice boundaries together, a negative turn gets added. We started with two strings, A and B, and when we spliced them together, we made one string, A, B, V. Both strings A and B had a positive turn, and we removed one of them. Now let's think about what happens when we glue two graphs together. We do this by gluing together two half edges that are pointed in opposite directions, A bar and A. We will use an uppercase letter to describe the rest of the boundary. We call the left string B, A bar, and the right string A, C. When we glue the boundaries together, the half edges A and A bar will combine into a full edge, and a negative turn will be added. We now have a very simple formula for describing gluing. If we glue a graph with the boundary AC onto the half edge A bar, this will replace the half edge A bar with the string VC. Or if we glue the graph A bar B onto the half edge A, this will replace A with the string BV. I call this a branch gluing operation. A branch with a single straight edge has the boundary A bar A wedge. If we glue this graph to another graph, it has no effect, as we can see from the formula. A graph with just a dead end will have the boundary A wedge or A bar wedge. If we glue this graph to another graph, it will remove a half edge from the boundary, as we can see in the formula. In addition to branch gluing, there's another operation called loop gluing. In loop gluing, we create a loop when the path is turned plus or minus 360 degrees. Imagine we have a graph with two opposite half edges, A and A bar, and there's a 360 degree turn between them. We can glue together A and A bar to form a closed loop. Anytime you see the string AA bar, you know that the path has turned 360 degrees clockwise, and you can glue the half edges into a loop, and this will remove the string AA bar. But the path could have turned counterclockwise. If you see the string A bar V A wedge, you know that the path has turned 360 degrees counterclockwise. You can glue the half edges together into a loop, and this will remove the string A bar V A wedge. Branch gluing is actually equivalent to splicing the boundaries together and then doing a loop gluing operation. Or you can even think of this as two splice operations that create an interior loop that is then removed. Up to this point, we've focused on two-dimensional shapes, but how does the graph boundary work in other dimensions? If you have some n-dimensional region, its boundary is an n-1 dimensional object. 2 points can bound a 1D curve. A 1D curve can bound a 2D surface. A 2D surface can bound a 3D volume. We've mostly been focused on 2D shapes. Here we're dealing with 2D regions divided by line segments. The boundary of a 2D surface is a 1D curve. The boundary is actually a circular graph. The edges of the boundary were originally the faces. The vertices of the boundary were originally half edges. The reason we can describe the boundary as a 1D string is because the boundary is one-dimensional, and we could circularly shift the string because the string is describing a circular graph. When we extend the algorithm to 3 dimensions, we are dealing with 3D volumes that can be given different colors, just like the faces. The boundary is now a 2D surface that encloses the 3D volumes. Again, we lose a dimension when we go from the 3D shape to its boundary. The 3D volumes become 2D regions on the boundary. The 2D faces become 1D curves on the boundary. The 1D edges become zero-dimensional points on the boundary. The boundary is a graph. If there are just 2 volumes, the boundary will be a circular graph, and we could describe this with a boundary string. But if there are more than 2 volumes, the boundary won't be a circular graph, and we cannot use a one-dimensional string to describe it. The boundary will be a planar graph. For 2D shapes, there are 2 basic ways of combining graphs together. We can glue the edges of the graph or the faces of the graph. When we glue the edges together, that's a branch gluing operation. When we glue the faces together, we are splicing the boundaries. For 3D shapes, there are 3 basic ways of combining graphs together. We can glue 2 edges together, or 2 faces, or 2 volumes together. Let's think about what happens to both the original graph and the graph boundary. When we glue together 2 edges of the original graph, we are gluing together 2 vertices of the boundary. When we glue together 2 faces of the original graph, we are gluing together 2 edges of the boundary. When we glue together 2 volumes of the original graph, we are gluing 2 faces of the boundary. This gives us many different ways of combining the graphs together. This will be very important later when we create the grammar rules. We're going to try combining various graph boundaries to match a particular graph boundary. We've now talked about the graph boundary and how to cut and glue graphs. Now let's get back to the algorithm. The first thing we do is we take the input shape and cut every edge in half. Once we do this, each vertex of the input is disconnected from the other vertices. Each of these disconnected pieces is a new graph, and we call these graphs primitives. They're the most basic building blocks we use to make new shapes. Any shape you build out of these primitives will be locally similar to the input shape. After disassembling the input shape into small pieces, the next step is to reassemble the pieces together into new shapes. I'll explain how by gluing these pieces together, you can create every possible locally similar shape, and how to organize the shapes into a graph hierarchy. This by itself is an important contribution to my work. The The hierarchy is made up of generations. Each new generation is calculated by taking the previous generation and performing gluing operations. If the hierarchy were continued forever to an infinite number of generations, it would contain every locally similar graph. Now, this would be impossible to actually compute, so you should think of this not as a concrete data structure that we're going to compute, but rather as an abstract concept. Later, when I talk about how to implement the full algorithm, I'll explain how we remove parts of the graph hierarchy. So we won't have to construct the full hierarchy. We'll create just enough of it to make the graph grammar. The hierarchy is kind of like a family tree for graphs. Each graph has a set of children and a set of parents. But the term tree is misleading here because computer scientists use the term tree to refer to a data structure in which each node has only one parent. So the hierarchy is not actually a tree because two siblings can have the same child. A graph's children are found by trying every possible way of gluing it to a primitive and every way of loop gluing it. To find the parents of a graph, we try cutting every loop and cutting out any primitive that we can. The graph hierarchy is made up of generations. Generation 0 contains the simplest graphs, which are just edges. Generation 1 contains the primitives. Each new generation is found by taking the previous generation and by gluing primitives to the graphs and loop gluing when possible. Each generation gets more and more complicated. If we continue this hierarchy forever, it would contain every possible locally similar graph. When we construct the graph hierarchy, we have to be careful not to add duplicate copies of the same graph. When we construct the hierarchy, we are performing many gluing operations, but the order of these operations does not matter. You can glue the pieces together in any order and get the same result. Imagine we have a graph, and this graph has two children, and those children share a child. The top graph is the grandparent. The bottom graph is the grandchild. There are two gluing operations in this diagram. We'll call them Operation A and Operation B. We can construct the grandchild from its grandparent in one of two ways. We could perform Operation A, then B, or perform B, then A. There's a procedure we can run to check that we're not adding the same graph twice. Before we add a graph to the hierarchy, we find all of a graph's parents. Now we do this by going back to each of the graph's grandparents and by reversing the order of the two operations from grandparent to grandchild. If the new graph has already been added as a child to one of its parents, then we don't add it again, since it's a duplicate. Normally, we can reverse the order of the gluing operations, like this. But sometimes there's a complication. Consider a graph with a loop. This graph has these two parents. Ordinarily, the parents of a graph should share a grandparent, but in this case, they don't. This is because, if you think about it, a branch gluing operation really consists of two parts. First, we add a primitive, and then we glue it to the graph. If we separate the branch gluing operation into these two parts, now we can find a shared grandparent. Again, we can construct the grandchild from the grandparent by either performing Operation A first, then B, or B first, then A. A graph is complete if it has no remaining half edges left to glue. A complete graph always has the boundary string wedge. Our goal is to create complete graphs. One approach we could take is to randomly glue primitives together until we reach a complete graph. This works fine if the input graph is a tree with no loops. But for inputs with loops, this is a very bad, inefficient way to make graphs. For example, let's begin with this input shape and try to construct graphs by gluing primitives together. But it soon becomes very difficult to know how to complete the graph. Or here's another example where it becomes impossible to complete the graph. A better way to construct graphs is to use a graph grammar. A graph grammar can produce the same graphs, but it's much more efficient. And we don't run into this problem where we don't know how to finish the graph. In this video, I've covered the first part of the algorithm. We started with an input shape. We cut the input shape into small pieces called primitives. Then we glued those primitives together in every possible way we could, and we organized the possible combinations into a graph hierarchy. In my next video, I'll dig into the next part of the algorithm, which is really the heart of the algorithm, where we create the graph grammar. If you like this video, please click subscribe.